In this video, I want to show you how you can write your own resist model for HyperLith as a plugin. Here is the basic flow of HyperLith. You have the mask model, and that simulates the mask, and you get the scattered orders that go into the imaging model, and that creates the image in resist, or the aerial image, and that goes into the resist model. Here we have various resist models: full physics, CALPM, stochastic, CM1, and there's a plugin option. Then your resist model could optionally send the resist surface to the SEM model. And all of this data produced by all of these simulators, these models, can be output and measured, plotted, and analyzed. So the benefits and features of a user-written resist model: you can conduct your own research into new resist models. You can keep your model secret or proprietary. You can use the entire HyperLith infrastructure. In other words, you don't have to do all the work to calculate the image in resist. And we also provide excellent tools for measuring and analyzing. You can expose your resist model's parameters just as any other yellow fields in HyperLith. And you can use the tuner to calibrate your resist models to actual data, just as you would any HyperLith resist model. You can code your plugin in Java or Python, and so there's many powerful libraries that you can use. So this is an option to HyperLith. So when you buy HyperLith, you can buy the resist option, which you need, and if you want to, you buy the ARMY option, Advanced Resist Modeling Infrastructure. That includes the tuner, where you can do normal tuning, CD-based tuning or contour-based tuning, and the user-written resist model. And that's what we're talking about today: your ability to write your own resist model. Okay, let's see how to get started. So let me show you how this works. We'll set up a new HyperLith simulation here. And we choose the EUV low NA contact array. Well, let's just choose a line to start with. And an EUV stepper model. And for the resist model, instead of choosing one of the models that we offer that come with the resist package, you choose the user-written resist model, UWRM for EUV. Okay, so now the way this works is this is just regular HyperLith. We can, here's your mask, here's your aerial image, and the resist is giving an error because we haven't set up the user-written resist model. So we've got the user-written resist model, UWRM, chosen, and then there's parameters here. This is the N and K of the resist, but the model is actually here. So what you do is you tell where the jar file is if you're programming in Java, or you say where the Python file is. Actually, it's not a Python file, it's an executable that runs a Python file. So in this case, we're going to load this. We're going to point HyperLith to this command line tool that executes a Python program, and I'll show you that next. So once we run that, or once we point HyperLith to it, it loads the resist model. Now this is the user-written resist model, and this resist model exposes parameters to you, and you can change those parameters. So just like a normal resist model will dose to size, okay, and then we can change a parameter. You can set your Gaussian blur. So let's choose a different pattern. Let's say an elbow. Okay, and we'll see what the resist model gives us. Okay, so the resist model finished, and we have this. We can change, for example, the Gaussian blur. And again, these are parameters that your script exposes. Okay, so let's look at how the script works. Okay, so this is the program that you point HyperLith to. Okay, this is, you can call it whatever you want and point to it, but what this does is it sets up your Python environment and then executes a Python script. The Python script is what you write. That's where your resist model is. Your Python script has to subclass this PyResist, and we provide you this. Okay, so you subclass that, and you can see what it's doing. It's very easy. There's a bunch of methods that you need to implement, and they're pretty self-explanatory. Get resist model name. Okay, so this is called my Python resist model number 1. Okay, requires a film stack. So is it operating on a thin aerial image or a thick aerial image? Requires thick image. So you could use a film stack but still have a thin image that's just taking a slice. Returns thick result. Okay, so these are, now here's a key one, get knob names. So actually we were running this one, this Python example 2, and the knob names were DILC, Gaussian blur, positive or negative tone, and base quencher. And if we look back at HyperLith, you see DILC, Gaussian blur, base quencher, and M0. And then its default values. It's returning one intermediate result. And then here's the actual code to simulate the resist. You get the image as a 3D NumPy array, the number of cells in X, number of cells Y, number of cells in Z, LX, LY, Z, the dose, and the knob values. That's the values the user chose for these knobs. So in this case, we copy the knob values into these variables, and we do a few operations where this is the exposure here, creating a PAG field, a field of PAG, and then the acid is 1 minus the PAG. Then we, for diffusion, we use this library. This is just a 1-line call or 2-line call with the Gaussian filter, which is in SciPy, and we do a Gaussian blur, and then we calculate the amount of deprotection, and then we return this t function. And the t function is a level set function such that t equals 1 is your resist surface. And so then we return the t function together with the base, the amount of base quencher that's left. That's an intermediate result. And we return a 4D array. Okay, and that's it. So you can write your own resist models easily and use all of the power of HyperLith. You know, you could set up your blur as a variable. Blur, discrete range, 0 to 10 in steps of 2.5, and run your simulation. Let's turn off focus and dose variation. And it's running 5 times it's calling the user written resist model. And then the results will show up here just like they would be if you were using our own resist models. All right, and now here let's look at the aerial image, or sorry, the resist pattern for the different amounts of blur. Okay, no blur, 10 nanometers blur. Another thing I should mention is that you can this also works with SimRunner. So you can create a new launch SimRunner mode. We'll say 4 instances. And we'll run the simulation. And each of the PSSs is able to contact the Python and start the Python script, and now they all run at the same time. And if the PSS is on a remote machine, as long as you've configured your Python environment to be accessible on the remote machines, you can also use it with SimRunner on a remote machine.